Assalamualaikum warahmatullahi wabarakatuh and very good morning. So today we are going to continue on chapter 5. So today will be our first lesson for chapter 5. Okay, in chapter 4, we have learned how to find the size of a flow reactor and also the time for a batch reactor, whereby we know already the rate law. It means that we can write the rate law. For example, RA is equals to KCA. We know that CA is equals to 1. This is an example. And we also know what is CA based on chapter 3, stoichiometric table. So that's what we have learned in chapter 4. So for chapter 5, we focus on how do we write the rate law, where we need to find the K and also the order. So for example, KCA to the power of alpha, what is alpha? And what is the value of K? From chapter 1 to chapter 4, all the question K was given. Or even if K was not given at the exact temperature we are doing the experiment, the K value for another temperature of the same reaction were given. But in chapter 5, we have to find the K, we have to find the order. So for a reactor, batch reactor, concentration and pressure and or volume are usually measured and recorded at different time during the course of the reaction. So usually if it's a liquid, then you find the concentration. If it is pressure, then you find it's for the gas. So there are cases also you find the volume over time to find the specific rate constant, which is K, and also the order of the reaction for you to be able to write the rate law. Okay, in this chapter, we're going to learn several methods. In general, there are 4 methods, which are differential method that we're going to learn, integral method, initial rates method, and also half-lives method. However, for differential method, among all the method of differential, we're going to learn graphical and numerical. So in total, actually, we are going to learn 5 methods. Graphical for differential method, numerical for differential method, integral method, initial rates method, and also half-lives method. So based on the data, where we varies the concentration or also pressure over time, we're gonna generate a data to find our 2 things. The first one will be specific reaction rate, our K. Second one is our order of reaction. For example, we have the reaction between A and B to get a product. We're going to write the rate law as minus RA is equals to K C A alpha C B beta. So chapter 5 will help us to figure out, to find what is the value for K, what is the value for alpha and beta. Then we can write the rate law. Aside from that, we also will learn how to find the K by knowing the activation energy and also frequency factor from the Arrhenius equation. So, okay, in the batch reactor data, experimental batch reactor usually are operated isothermally, T equals to T naught, and at a constant volume. Okay, because we have a reactor that doesn't change the shape, as it is easy to interpret the result. So you can imagine you go to a lab, you have a size of a beaker or a size of like a reactor. The volume will always be constant. Okay, and you control the temperature. Commonly, the determination is achieved by measuring the concentration as a function of time. This is for liquid, or pressure time data for gas phase reaction. So experimental data also used for the determination of temperature dependency in reaction using Arrhenius equation. I think this one I have already explained in our previous class. Okay, let's go to our first method. So as I mentioned before, differential method, there are 2 methods, graphical and also numerical. So let's see what is our differential method. Okay, so there are several things that we have to know. first one, this method can only be used for a case where the reaction is irreversible. For example, A is converted to end product. And in this method, we are going to determine the reaction order, alpha, if it's KCA, and also the specific rate constant, K. How do? We numerically differentiate C versus T data. See, we have here minus RA in numerical form, in differential form, will be minus because it's disappearing. The differential of concentration of A, our reactant, over differential of time, so is equals to KCA. Then we will find our K and also our alpha. And these cases is only applicable when the reaction condition are such that the rate is essentially a function of the C of only one reactant. So if we have a case, for example, we have a decomposition case where we have one reactant lead to several products, then no problem. But what if we have two reactants? We have A plus B. How do we apply this differential method? What do we do? If in the case of we have two reactants, A plus B to get products, we're going to use method of excess. So what does this method of excess mean? By the name, we can understand that method of excess means that we're going to make one of the reactant in excess. Okay, so it's possible to determine the relationship between minus RA and the concentration of other reactants. So for a reversible reaction involving A plus B, suppose the rate law is minus RA is equals to Ka Ca alpha Cb beta. Because there are more than one reactant, in order for us to fulfill the requirement for a differential method, we will make one reactant in excess because alpha and beta are both unknown. So to determine what is the step, to determine alpha and beta, we're going to make two set of reaction. So the first set of reaction, what do? We make reactant B in excess. So when reactant B is in excess, CB is equals to CB naught. Over time, the amount of the amount of the concentration of B doesn't change over time. So CB is equals to CB naught. K is also a constant. So since KCB is equals to KCB naught, they are constant, we can represent them by K prime. So we replace it in the equation. Now the equation of the rate law is simplified into minus RA is equals to K prime CA alpha. So now in this case, yeah, we can do differential method because we only have one concentration. Okay. Step 2, after we do the experiment, we determine already alpha. So we have skipped several steps actually in between. So we do something, we do the differential method, we find the alpha. After this, I'll show you how we do the differential method. So we already find the alpha. And the second set of reaction, we're going to make A in excess. So when A is in excess, similarly as just now, KCA going to be equal to KCA naught. So since it's a constant, we can represent KCA naught or KCA as K double prime. So we can simplify the equation into minus RA K double prime CB beta. So from this second set of reaction, we're going to find beta. First set of reaction, we got alpha. Second set of reaction, we got beta after we do the differential method. Then we have to find Ka. So we find Ka from this formula where we rearrange the equation of minus Ra. Suppose minus Ra is equals to Ka Ca alpha Cb beta. We rearrange to find Ka. So we know minus Ra, we already know our alpha and beta. So at one set of reaction where we know the minus Ra value, we know the concentration of A, we know the concentration of B, we put into the equation, we're going to find Ka. Hence, we can rewrite the rate law as we know already the value for Ka, the value for alpha, and the value for beta. Okay, so, all right, just now we have skipped on the differential method. How do we find the alpha and beta? Here, I'm going to show you how do we do the differential method to find alpha and beta. So we're going to focus on only one reactant lah, but you can do the method of excess to find beta. We're going to do the same step. Okay, let's say we have a reaction. It is carried out isothermally in a constant volume batch reactor, and we recorded the concentration as a function of time. So if we write the rate law, it will be minus RA equals to KACA alpha. And in differential form, minus RA is equals to minus dCA over dt. Minus because of the disappearance of reactant A equals to KACA. So what do? We have this minus dCA over dt equals to KCA alpha. We're going to linearize it into linear form. So in linear equation, the standard equation would be y is equals to mx plus c. We have to change it into linear form. So how do we change it into linear form? We add the term ln on both sides of the equation. So we add ln on the left-hand side, we got ln minus dCA dt. And then on the right-hand side, we got ln kCA alpha. So we can expand the right term. So when we expand, we got ln k plus ln CA alpha. We move alpha to the front, we have ln k plus alpha ln CA. And writing in the form of y equals to mx plus c, we just change the sequence of alpha ln CA with ln k. We have y equals to mx plus c, where y equals to ln minus dCA over dt, minus here. Alpha is our m, x is our ln CA, and our intercept c is ln k. So we have the slope m alpha, we have the intercept c as ln k. So we can find our alpha and also ln k when we draw a linear graph, okay, by finding y value ln minus dCA over dt and also x, which is ln CA. We have to plot the graph lah. So see, just now I mentioned, we have to write the rate law into linear form. So we already write into ln minus dCA over dt as our y equals to m, our slope is alpha, x is ln CA plus ln k, which is our intercept. So when we plot y-axis, which is ln minus dCA over dt, versus x-axis, which is ln CA, from this slope, we can find alpha, alpha is the slope, and then we can find the value of ln k from the intercept. Okay, so that's basically at the end. All right, now we have to find our y and our x. Okay, in order to find our y, which is our differential equation lah, minus dCA over dt, in order to find that, there are actually several methods, which are graphical method, numerical method, and polynomial fit. But for our class, we're going to learn graphical method and also numerical method. Remember that from the experiment, we are only given the value of time and also concentration. So we have to convert it into dCA over dt through differential method. Okay, let's see the first differential method, which is graphical method. Okay, this is the first method for differential method, which is called graphical method. So in the graphical method, so in this table here, x represents time and y represents concentration of A, because we are considering only one reactant, which is A lah. So here we have x, which is time, and y, which is concentration. So we have to construct the table. We write down the value of x and y, which is usually given or we get from experiment. Then we have to find the changes of x and also the changes of y by simply deducting. So for example, this part is x2 minus x1. So we got the changes here. y2 minus y1, we got the changes here. And so on. We find the difference between x here, we got this part. We find the difference between y here, we got this part. Then we have to continue by finding difference of y over difference of x. The value of difference of y we get from y2 minus y1. Difference of x we get from x2 minus x1 for the first row. So we can find difference of y over difference of x for each row. Okay, so if we have 5 set of data, there will be 4 difference. Then, how do we convert the changes into dy dx? So in order for us to convert, what we need to do is, okay, just observe here, this is 2, 3, 4, 5. We don't start with 1. Okay, how do we find dy dx? Okay, for graphical method, what we are going to do is we have to plot a histogram. So remember back, we have x1, y1, x2, y2, and so on until x5, y5. So we have to plot changes of y over changes of x versus x. So changes of y over changes of x is our y-axis, x is our x-axis. So we have here x1 until x5. If the data just now, it can goes until x7, for example. Then we plot a histogram. So x1, x2, we know actually the value. And what is the maximum value here? That will be our changes of y over changes of x. Just now here, changes of y over changes of x for second would be this part, where x2 minus x1. So changes 3 will be this part. This is changes 4 and changes 5 because the data just now given until x5. Okay, so we plot the histogram. So in order to plot histogram, remember you need to know x and you need to continue finding the difference of y and also difference of x. So after you plot the histogram, you draw a smooth curve, a purple smooth curve that connect the histogram as much as possible. Then what do? The point where the purple curve cross the green histogram vertically, like here for example, x2, it crossed with the purple line. So this one will be our dy dx2. Okay, because this is changes of y, changes of x2, the first histogram. The second histogram is changes of y over changes of x3 that involve x3. So where the value of x3 vertically cross vertically cross the purple curve, you're going to get dy dx3 and so on lah. Okay, through that you can complete this table. You can find dy dx 2, 3, 4, and so on. So after that, okay, now you only have dy dx. In our case, we have actually d concentration over dt. It didn't complete yet. Remember, we want to find the constant, which is k, and also order alpha. So this does not settle yet. Now we're going to see an example where we settle it until we find the order and also k. Okay, but now we already know how to draw the histogram and find dy dx from the histogram. Let's see an example. We have an example 1. Determine the order of reaction alpha and specific reaction rate k from batch data for reaction A converted to B. So we were given the time and also the concentration. Okay, let's go back. So basically, we want to write a rate law. We want to write the rate law of this reaction. We know that since it's involved only one reactant, then the rate law is minus RA is equals to Ka Ca alpha. And when we write in differential form, minus RA is equals to minus dCa over dt, and it's equals to Ka Ca alpha. Okay, so we want to linearize this equation so that we can find alpha and k from the intercept later. So we linearize it by adding the term ln. Just now I already showed you. You can go back to that part and recheck if you want to revise it again. Okay, so now you have this term. So later on, what you need to do is you have to draw a curve where the y-axis is ln minus dCa over dt. The x-axis will be ln Ca. However, here we have t, we have Ca. Ln Ca, yeah, we can simply calculate using calculator. But minus dCa dt, we have to use the graphical method. as the first method. So we have to find minus dCA dt first, then only we can do another plot. So based on this data, given we have time, we have CA, we have to tabulate, okay, tabulate, find our changes of Y and changes of X. So here we have changed time 0, 3, 5, and so on. Concentration of A is 4, 2.89, and so on. Then we find minus changes of C over minus changes of T. Why suddenly minus when this one is positive? Okay, because remember back, in this equation, we want to plot later on ln minus dCA over dt equals to alpha ln CA plus ln K. So in the y-axis, the term is in minus form. That's why we can simply add the minus term. So what happened? So we find the minus, the changes of t first. So 3 minus 0, we got 3. 2.89 minus 4 is a negative form. However, since we add minus here, so minus minus, it becomes positive. So this is minus changes of C over changes of T. So it becomes positive. All the term become positive since the concentration actually reduced by time. Okay, now we have to find the minus dC over dt, the differential form. In order to do that, we do the graphical method. Okay, graphical method, there are 5 steps in total actually. The first step is we have to plot minus changes of C over changes of time versus time. So here our x-axis is time. We have data 0, 3, 5, 8, and so on. So 0, 3, 5, 8, and so on. And then our y-axis will be changes of C over changes of T that we have calculated just now. This 0.37, 0.37, 0.32, 0.32 for the second histogram, and so on until the following histogram. So we have plotted the histogram, okay? If we have 1, 2, 3, 4, 5, 6, 7, 8 data, if we have 8 data, then we're going to have 7 histogram divided by 1 lah. So we have 7 histogram here. 1, 2, 3, 4, 5, 6, 7. So first step, plot minus changes of C over changes of T, already in form of minus, versus time. Then what do? We draw a small curve. See the purple curve? So you can draw better lah. After we draw the small curve, we find dCA over dt. You can see here the green color. dCA over dt, sorry, it should be minus dCA over dt. I forgot the minus, but it's supposed to be minus dCA over dt lah. So if we have minus dCA over dt here, then minus dCA over dt is actually the cross section between the value of x here to the curve, the purple curve. So here we got minus dCA over dt for this point, and this is minus dA over dt for the following point. So from there, we have several value of minus dCA over dt. This is minus. So what do? We plot. Here we plot the graph of ln minus, again, I forgot to write, minus dCA over dt versus ln CA. Here you can see the green box is the ln minus. See, there is a minus here. dCA over dt versus ln CA. Then the fifth step, we can find the rate coefficient from the slope and intercept. So our slope will be order and the intercept will be our ln K. So remember, for graphical differential form, we basically have to draw two figures. The first figure is the histogram to find minus dCA over dt. Then we have to continue by plotting ln minus dCA over dt versus ln CA in order for us to find alpha, the order, and also ln K from the intercept. Okay. So once settled, we can write the rate law lah. Okay. So that is the first method. Then we have the second method of differential method, which is called numerical method. So based on the name itself, it's basically, we're going to find the value of alpha and also ln K letter through formula calculation. However, this is only applicable for uniform sampling interval, which means the time should be uniform, the increment of the time. So we have time, we have concentration, the increment should be uniform. So in the end, we need to plot the graph of ln minus dCA over dt versus ln CA to find alpha as the slope and also ln K as the intercept. So instead of finding minus dCA over dt through the graphical method, we find this minus dCA over dt through numerical method. So that's the difference. So step 1, 2, 3, this one, step 1, 2, 3 will be replaced with numerical method, but step 4 and 5 will be continued as usual. Okay, so we have to, later on, we have to draw ln minus dCA over dt versus ln CA plot, but ensure that the increment is uniform. Like our example just now, 0 plus 3 got 3 and then plus 2 got 5. So the increment is not uniform, hence our previous data cannot be used for numerical method. Okay, let's say we have another set of data where the increment is uniform. Then how do we find this dCA over dt? Notice that the equation here already write how to find dCA over dt, but it's in a positive form. Later on, you have to make it minus lah. So initial point, dCA over dt in positive form, it's equal to 3 minus 3 CA naught plus 4 CA1 minus CA2 over 2 changes of T. Where do you get this? Here you already have the time, you already have the concentration. So the first time will be T naught, second T1 and so on. The first concentration will be CA naught, second is CA1 and so on. So minus 3 times CA naught is here, plus 4 times CA1 is here, minus CA2 is here. And then over 2 times changes of T. So T1 minus T naught, you got the changes times by 2. That is for initial point only. Last point, we're going to focus at the end. So dCA over dt, not minus yet, for the last point would be CA3. So here, if it is until, okay, it's until CA5. So CA3 minus 4 CA4, this is CA4, plus 3 CA5 here, over the changes of 2, over 2 times the changes of time. So T5 minus T4 is the changes. Since it's uniform everywhere, the changes is the same actually. So we got the bottom line. So let's say there are more data. Then this last point is only applicable for the last of the data point lah. Since here we have 6 set of data, we end with CA5. How about the intermediate? So for intermediate, how do we find that this CA over dt? It's equals to, for example, this part, CAI plus 1. Okay, so that's, for example, we have CA2 minus CAI minus 1, CA naught, for example, then divide by 2 delta T. So when we want to find CA1, dCA dt, T1, okay, T1. So if we want to find here the changes, then CA1 plus 1 is 2, CA2 minus CA1 minus 1. 1 minus 1 is 0, so CA naught over 2 changes of T, which means if we want to find dCA over dt at this point, we're going to use CA2 and CA naught. If we want to find the dCA dt at CA2, we're going to use CA3 and CA1. If we want to calculate dCA over dt at point 3, we're going to use CA4 and CA2. If we want to calculate dCA dt at point 4, then we're going to use CA5 and CA3. Okay, so that's for the intermediate lah. So this is an example. Determine the order of reaction and specific reaction rate. So alpha and also K with respect to triphenyl methyl chloride from batch for data for reaction. This is the reaction. We have A plus B to get C plus D. It was carried out in a solution of benzene and pyridine at 25 degrees C. Pyridine reacts with HCl that then precipitate as pyridine, hydrochloride, thereby making the reaction irreversible. So we have irreversible reaction. And this is the concentration versus time table. So we have 1, 2, 3, 4, 5, 6, 7. We have 7 set of data. And we can see here that the increment is uniform. Thus, we can use the numerical differential method. Okay, so we're going to use the differential method with the initial concentration is 50 at time 0. Okay, so what do we do? Remember back, in the end, our target is to write the red law because we're going to find K and also alpha. What do? We have to linearize the equation into this form. This is for step 4 and 5 later. So first, we're going to find the value of dCA over dt, and then we have to change into minus form. Then we complete this equation lah. We have time, we have concentration, we find the initials, the initial data, dCA over dt at time equals to 0. We're going to use the 3 set of data lah, 50, 38, 30.6. So this is the value. We're going to use the equation I have shown just now. We got the value of dCA over dt. Then we find the intermediate. Okay, we find the intermediate using the second set of equation. Now we do for all form except the final form. So we have 7 data, 1, 2, 3, 4, 5, 6, 7. We have 7 data, we're going to have 5 dCA, 7 data, we're going to have 6 dCA over dt. Similar like the graphical method just now, we have, if we have 7 data, then we will draw 6 histogram. So here we have 6 lah. Okay, so we have 6, but we start with t equals to 0 in this case using the equation. So dCA over dt until 6. Okay, so we have to use the final equation for the last one lah. This is our final equation. So after we do for all point, we just tabulate the data in order to ensure that we don't make any mistake. Okay, so just now graphical, yeah, the histogram, we have less 1 changes, but remember for the first point also we can calculate minus dCA over dt, so it become equal lah. Just now I said differently. Okay, now time CA was given from the question. Okay, you can change into CA not in times to the power of 3, so you change all the value. Then you find ln CA first. Ln CA is for completing the x value lah, because later you want to plot the y equals to mx plus c graph from ln minus dCA over dt equals to alpha ln CA plus ln k equation. So you find ln CA. Then you want to complete for this y part, find dCA over dt using equation just now. So using this equation, see, we have 2.86, we have 1.94. So we have all the value. Okay, all the value is in negative form because it's dCA over dt. Then you have to change into minus dCA over dt, so all become positive. Then we change into ln minus dCA over dt because that will be our y. Okay, we got all the value, so we have the y-axis, our x-axis is our ln CA. Okay, so until here is our first step, second step, third step. Now plotting is the 4th step. After we plot, we can find our alpha from the slope. So we got 1.9959, and also we can find our ln k from the intercept. So here we find our ln k. Okay, that's all for the differential method. We have learned the graphical differential method and also numerical differential method. All right, in our next class, maybe we can learn some of the exercise. Okay, thank you very much, everyone.